Welcome back, everyone. We're going to review just quickly what we learned, or you hopefully learned in the previous video, and then relate this to the pH scale. So most everybody's heard of pH, okay? And when I see the word pH, I think of the power of hydrogen. Okay, that's what pH stands for, and the technical term is actually the potential of hydrogen. So if we think about what this means, um, when we are looking at H plus concentration or hydronium concentration, we know that this means acid. That's what we want to think about right away, is that corresponds to an acid. And so we learned in the previous video that water is neutral. And so experimentally, we found that the ion product constant, Kw, okay, equals 1.0 times 10 to the negative 14. Okay, and so when we look at water, we know it can react with itself, and we have equal concentrations of hydronium as well as hydroxide. Okay, and so because we have equal concentrations, that means that we have a neutral solution. Okay, and so I'm going to write this out, and it's going to Okay, so we worked problems in the last video using this. All right. So experimentally, we know that water is neutral. It has 1.0 times 10 to the negative 7 concentration of hydroxide, and the same for hydronium. So we think of hydroxide as a base and the H3O plus, or proton, however you want to think of it, as the acid. Okay, and that is always equal to 1.0 times 10 to the negative 14. All right, so we can now relate this to the pH scale. Okay, and so we'll look at that scale in a minute, probably heard of this before, but we relate it by a logarithm. So the pH is equal to, so the power or the potential of hydrogen is equal to the negative log of the hydronium concentration. Okay, so we're looking at the power of hydrogen in this situation. All right, so the lower the pH, the higher the concentration of H3O plus, right? So if you have more hydronium, that means you have a more acidic solution. Okay, and so your pH is going to be less than 7. All right, so we know that water's neutral and it has equal concentrations of our hydroxide and hydronium. Therefore, the pH is 7, right? It's neutral. Okay, neutral solutions, pH is 7. If it's acidic, it's going to have more acid component, right? H3O plus. Okay, and this makes the pH less than 7. If we have a basic solution, our pH is going to be greater than 7, okay, but the hydronium concentration is going to be higher than the hydronium concentration is going to be less than 1 times 10 to the negative 7. Okay, and so there's going to be a higher concentration of hydroxide here. Remember, because bases have more of this in the solution. All right, so this is how we can relate. So pH and hydronium concentration are related by the negative log. So they have an inverse relationship. The more hydronium concentration you have, the lower the pH. Okay, and so we can look at this as sort of a scale of 0 to 14. And here it just shows you things that are acidic. So you've got, of course, lemons and strawberries and fruits, and milk is even on slightly the acidic side. So anything below 7 here is acidic. So the higher the hydronium concentration, the lower the pH. 7 is neutral, okay, and then anything above 7 to 14, This is the basicity increases, so anything like stomach medications, Maalox, ammonia, Clorox, these are all basic components. So here's our scale. It's from 0 to 14. All right, so let's do some calculations with our new formula that we know is pH is negative log of the hydronium concentration. All right, so a logarithm has the same number of places after the decimal as there are digits in the original number. Okay, and so if you look here, we have two numbers. Okay, and so it says that we're going to have that many places past the decimal. So the best way to see this is just by an example. So if you're given the hydronium concentration of a solution and we want to know the pH, so we're going to take the negative log. Okay, this is where you need to get your calculator out and be sure, okay, you've got to hit the negative key on your calculator, not the subtraction key. Hit the negative key and log. And most of you may need to put this in parentheses. So 1.2 times 10 to the negative fifth. Okay, you should get 4.92 when you put that number in. Okay, we have two digits. Therefore, we're going to have two decimal places in our final answer. So we have 3 sig figs, but we have 2 decimal places. That's how it's reported here. If you have 2 numbers, then you carry your answer out to 2 decimals. Okay, and so the pH is 4.92. Okay, now think about it. Does it make sense? Okay, look here. My hydronium concentration is more than 1.0 times 10 to the negative 7. Remember that negative number there. Okay, if it's a negative 5, that's more than negative 7. Okay, so I have more hydronium concentration, so I would expect, since hydronium means acidic or acid, that I'm going to have an acidic solution. And that is correct. It's 4.92. So if I look at my scale, anything less than 7, so it would fall somewhere in here, okay, is acidic. So go back and look at your answer and make sure that it makes sense, okay? All right, this is one that gets students. It's really just a mathematical operation. That's all it is, okay? And it's also being able to rearrange an equation, okay? So we know our equation is the pH equals the negative log of hydronium concentration, right? Okay, so there it is. All right, in this problem, we're given one value, but it's not the hydronium concentration. Instead, we're given the pH. Okay, so in the previous problem, all we did was take the negative log of the number that we were given. Here, we're given the pH, and we want to find the hydronium concentration. So like we've been saying through all these videos that I've been doing over all sorts of chemistry topics, that we can rearrange equations and we can solve for any of the variables as long as we're given all of them but one. Okay, and so we can do that. So this is just a mathematical operation. Okay, and so to do this in your calculator, okay, your pH is 8.50. So right away I know that this is a basic solution because my pH is above 7. Okay, then I rearrange. So the negative is moved over to the pH side. Okay, and then you have to do a calculation in your calculator. Okay, if you have a calculator like mine, okay, this is called the anti-log. So on your calculator, you've been using the log button if you were able to do the previous problem. Okay, the anti-log is typically when you push second function or a shift, okay, and it's the operation that's written on the calculator sort of behind the button, okay, and so on my calculator I push second function log, okay, and then it should show, you should see something that looks like this, okay, and that's the anti-log. So hopefully you've had this in your in your algebra classes and so forth. Okay, but you take the anti-log, so second function log of, and you can't forget that negative, negative 8.50. Okay, and you should get 3.2 times 10 to the negative 9 molarity. Okay, and so check your calculator, so it should look like this. I put it in parentheses just to make sure. Sorry, that was my phone went off. Okay, so you put second function log, that's the anti-log, of the pH, and then of course you have to put negative, so that's often forgotten, okay, because remember this is negative here, so your negative has to carry through here. Alright, so we have 2 decimal places, so report two numbers there. Alright, this makes sense. Our solution is basic, we knew that. Has a pH of 8.50. That means our hydronium concentration should be less than negative 7, and it is. It's negative 9. So it's a smaller number, and that makes sense because this is a basic solution, so we have less acidic hydronium concentration. Alright, so to relate this to the human body here, this is pretty interesting. Hey, we have to keep all of our the pHs in our body regulated, right? Okay, if the pH of our blood changes much at all, this can result in death. It has to stay at that pH of 7.4. Saliva is also acidic. Here shows your pancreas. Small intestine is basic. Here's urine, has a more wider range. Large intestines between 5 and 7. The stomach is the most acidic of what's listed here, of 1.6 to 1.8. So it's got HCl, hydrochloric acid, that's being generated in your stomach, your digestive juices there. But just to relate the pH scale to the human body as well. Alright, I'm going to do a separate video on some more problems, just so this video isn't too terribly long. So please watch the next video, and we will practice working these problems and even throw in one more type problem that I could ask. And I will see you in that video. Thank you.